Hi guys, Miss Venable here, bringing you a screencastify on nuclear chemistry. So let's take a look at some uses for nuclear chemistry. Lots of uses for this in our daily lives. First of all, of course, nuclear power plants. We have a couple of those here in North Carolina, but lots throughout the country. We're not building a lot of new nuclear power plants right now because they're so incredibly expensive to build, but they do give us green energy without carbon dioxide. There are a couple of hazards. You might be familiar with 3 Mile Island and Chernobyl and places where there have been nuclear meltdowns. But yeah, the benefits may outweigh the risks. Depends on who you talk to. Another use for nuclear chemistry is in medicine. We can actually use radioactive isotopes to act as tracers to identify tumors in specific organs, and we can also use it as a treatment for tumors. And we do use some radioactive isotopes in our daily lives, for example, smoke detectors. Smoke detectors have a radioactive isotope of americium, and without that isotope, smoke detectors would not work. And the last use is in food preservation. For millions of years, humans have been here trying to eat food. One of the problems is that food goes bad. And so in modern times, we have found ways to preserve our food for longer and longer and increase its shelf life. So food irradiation, I'll give you a few details on that. A couple of the isotopes that can be used are cobalt-60 or cesium-137. For example, irradiated milk has a shelf life of 3 months, and that's without refrigeration. So the U.S. Food and Drug Administration has approved food irradiation, and for lots of uses: beef, pork, chicken, shellfish, fruit, veggies, and spices. There is a little symbol that you can look for, and if you look, it's this little green symbol. Kind of looks like a plant in the middle, and then it's got some dashed green lines around the outside. And they are required to post if the food is irradiated. And nuclear imaging, I think, is one of the coolest in medicine. This is a thyroid CAT scan, and you can see that in a normal, healthy thyroid gland, this CT scan doesn't show much. But if you've used a radioactive tracer and that penetrates to the thyroid, then you can see much in a lot more detail what's going on in that gland when you go through the CT imaging. Pretty neat uses. Okay, so let's get into nuclear chemistry a little bit. So what do I mean if I say nucleons? Well, nucleons just mean the particles. So let's talk about the particles. And we know that the atom contains 3 subatomic particles: protons, neutrons, and electrons. And we're really more interested in the nucleus here, so we're going to be talking more about protons and neutrons. So radioactivity is instability of the nucleus. Also, one important thing is nuclear charge, because larger elements tend to be more radioactive. When we say nuclear charge, we're talking about the positive charge that's located in the proton. So really, we're just talking about how many protons. Okay, so a few details. You guys know this about protons, but they have a positive 1 charge each. They determine the identity of the element. So, if it's got 1 proton, it has to be hydrogen. They determine the atomic number, because that the number of protons is always the atomic number. The mass of a proton is about 1 AMU, and that's the number of protons is going to equal the nuclear charge. Okay, neutrons have no charge, 0 charge. They determine the mass of the isotope of an element, because if you have more neutrons, it's going to weigh more, but it's still going to be the same element. And the mass of a neutron is about the same as a proton, 1 AMU, and it's determined by subtracting the mass number for the element minus the atomic number. You can figure out how many neutrons are in it that way. Okay, a couple of examples. Sulfur has 2 isotopes. One of them is sulfur 32, and that would have 16 protons, and the remaining 32 would be 16 neutrons. So we just subtract 32 minus 16 to get the number of neutrons. Another isotope is sulfur 33. The mass, notice, is 1 more, so it's going to have 1 extra neutron in its nucleus. All of these isotopes would have a charge of plus 16 in the nucleus, no matter what, because that's how many protons. Okay, isotopes, atoms of the same element must contain the same number of protons, but the number of neutrons is going to vary. And so we have varying number of neutrons for the same element. We call those isotopes. To get the average atomic mass on our periodic tables, what they've done is taken a weighted sum of all of the isotopes for an element. And you would, to figure out the most common, you would just round that number. So the most common isotope here for rubidium would be 85, would have a mass of 85, would be the mass number for the most common isotope. So you just round up or down to get the mass number. And that generally that's the most common mass or the most common type. So what happens during radioactive decay is that some of these isotopes are going to have a nuclei that doesn't have balanced protons and neutrons, and it destabilizes the nucleus. And so the nucleus cannot stay together. The strong nuclear force can't hold it together. So a couple of different things are possible. It could just release some small particles and a little bit of energy. It could release a little bit bigger particle and a lot more energy. It could actually destabilize to the point where it sort of cracks like a cookie, just breaking in two. And of course, like a cookie, it's going to give off lots of other little pieces as well, little crumbs as well. So there's lots of possibilities for radioactive isotopes. So here's a couple of examples of radioactive isotopes. And actually, I think lead-207 is stable. And so is sulfur-32. So these are not all radioactive. They're just examples of common isotope masses. So the weighted average for zinc is 63.39. What would be the most common isotope? Well, you just round that down to 65. And cobalt, you would round down to 59 if you look at its atomic mass. Sulfur, you would round down to 32. Silver, you would round to 108. And lead, you would round down to 207. Actually, not up to 207. So one atomic mass unit, these numbers are in AMUs, actually has a mass of 1.66 times 10 to the negative 27 kilograms, but we've never really used kilograms for these. It's defined as the mass of 1/12 of a carbon atom. So the most common isotope is often also the most stable isotope, and therefore it is not radioactive, not always. So some isotopes are just naturally reactive. The natural decay process starts with a parent nuclide. It's going to spit out some particles and or energy, and whatever's left over is called a daughter nuclide. The daughter nuclide is always more stable than the parent nuclide. Now, you do need to know the cutoff. The cutoff is lead. There are some stable isotopes of the elements lighter than lead, but once you get past lead, every isotope of every element is always radioactive. Those heavier elements are very radioactive. So how do we know if something's going to be radioactive or not? Well, usually we'll just look on a chart. This little graph shows you a graph of the radioactive isotopes versus the size. So the number of protons is across the bottom. So as you go to the right across the bottom, the atoms will be getting bigger. And you can see that this little shaded area kind of goes and curves up. It's called the belt of stability. So past, atomic number 83, which is just past lead, there really are no stable isotopes. All of the isotopes are outside the belt of stability. So what does that mean for us? Well, it's all about ratios. So when you have smaller elements, the neutrons act like spacers for the nuclear force to hold together the repulsion of the protons, right? Because positives repel each other. So if the neutrons weren't there to act as spacers, then the protons would just repel each other and the nucleus would fall apart. But because there are neutrons there and they act like spacers, this strong nuclear force can kind of hold together all the protons in the nucleus. And we don't really understand the strong nuclear force all that well, but we know that it keeps the nucleus from just flying apart. So as long as the nucleus is pretty small, and we're talking about a pretty small element, there needs to be a 1-to-1 ratio of protons to neutrons so that you have one spacer for each proton. But when you get bigger elements, it turns out you need some extra neutrons. It's more like a 2-to-3 ratio. So you need 2 neutrons for every 2 protons. Okay, so let's get into how different ways that these radioactive isotopes can decay. And one way is through something called alpha decay. Alpha decay is the least harmful of all the different types of decay because an alpha particle is really just a helium nucleus. It's made up of 2 protons and 2 neutrons. It has this funny little Greek symbol called alpha. And what happens is your radioactive parent isotope will eject those 2 protons and 2 neutrons in the form of a helium nucleus. That's going to cause its atomic mass to go down by 4 and its atomic number to decrease by 4. And so we've written this nuclear equation here where we have uranium as the parent isotope. The arrow means it's decaying. It ejects a helium nucleus as a particle. There, we've written that at the end. You could write it as 42He, or you can write it as the alpha. Either way, it's a helium nucleus or an alpha particle. And the daughter isotope is what's left over. So the mass goes down by 4. Notice the mass goes from 238 to 234. And the atomic number goes down by 2. Notice it went from 92 down to 90. And so it's got to be a new element. It's not uranium anymore because its atomic number's changed. So if you look on your periodic table, you can look and see your atomic numbers, and you can see that thorium has atomic number 90. And so if I just do a little subtraction, 92 minus 90 tells me that it has to be TH. There it is, atomic number 90. So that is alpha decay. And by the way, when it changes into a new substance, that has a name. It's called transmutation. So alpha decay will always cause a transmutation and create a completely different element. Beta decay is also going to cause a transmutation, but the process is a little bit different. Beta decay has 2 different types. There's beta plus and beta minus. We are only going to look at beta minus in our class. We're also going to ignore some of the stuff that happens. One thing that happens in beta decay is there's an emission of something called an antineutrino. That's a little bit beyond the scope of this class, so we're just going to ignore that. Another thing that happens is an electron is ejected from the nucleus. Now, that's not possible because there are no electrons in the nucleus, but we're magically going to say that that occurs. It helps my nuclear equation work out correctly. To understand what really happens during beta decay is a little bit beyond the scope of our class. So we're going to pretend like an electron gets ejected from the nucleus. Also, as part of that, a proton magically becomes a neutron. No, I said that backwards. A neutron magically becomes a proton. So this weird kind of thing happens where the atomic number goes up by 1, but the mass stays the same. And you also produce a beta particle, which is just an electron. And the way that we write the nuclear symbol for an electron is 0 mass, 0 on top, and then an effective atomic number of -1. And then the symbol E for electron. It's not really a nucleon. It's like not in the nucleus at all. So here's the nuclear equation for the radioactive decay of carbon-14. And it converts into nitrogen-14. So the atomic number just went up by 1, and it ejects this electron. Another way to write that is with the beta symbol, the Greek letter beta. And this is considered beta minus decay because it ejects something that's negative. So that's why the beta symbol has that little negative right there. Okay, the last type is gamma decay. And the gamma symbol is kind of an upside down Y in the Greek alphabet. Gamma is not actually a particle. It's actually just pure energy radiation in the form of a photon of light energy and heat energy. It's the most harmful of all of them. It has a very high penetrating power. Usually gamma decay doesn't happen just by itself. Usually it follows alpha or beta decay. And what happens is you'll have a product in your alpha or beta decay, a daughter nuclei, that's excited. And what excited means is that the electrons that are in the outside that nucleus have jumped out to higher energy levels. And so what has to happen in gamma decay is that excited energy where those electrons are higher energy levels, it has to go somewhere. And just like in the emission spectrum for the hydrogen atom, when electrons drop down to lower energy levels, they have to release photons of light energy. And in this case, it's light and heat and kind of some hazardous stuff. And once they do that, the daughter isotope it'll still be the same nucleus, same atomic number, same mass, same everything, but it's just less excited. The electrons drop to a little bit lower energy level, and we call that the ground state. Okay, so I'll show you some nuclear equations later on. You'll have some assignments where you have to kind of combine alpha and beta decay with gamma decay and write the nuclear equations. Okay, this is a radioactive series because large radioactive isotopes don't usually stabilize just by one transmutation. They usually have to go through a whole long process, a whole series of decays until they form a stable nuclide. And this is actually uranium-238, a really common radioactive isotope that's used in nuclear power plants. And notice it goes through, I think it's 14 different transmutations or stages until it finally becomes lead-206 or 207, I believe, which is a stable isotope of lead. And that can take many, many millions of years for that to happen on its own. Okay, so how do we discover these particles, these amazing alpha beta particles and this gamma radiation energy? I said gamma particles, but really they're not particles. Well, it all came about because of charge. So if you take a radiation source that emits alpha, beta, and gamma decay, and you kind of shoot it like you're going to shoot a beam of light, and you put electrodes on each side of your beam. So you've got some positive electrodes at the top, and you've got some negative electrodes at the bottom, and your beam of light's coming through them. If they interact with those positive and negative electrodes, we'll be able to see that because they'll either deflect up. If they attract the positive, if they're negatively charged, they'll attract the positive electron. And as they're getting shot, they're like, ooh, I like you. And they kind of bend upwards. If they're attracted to the negative, right, because opposites attract. So if they're positive, they'll attract to the negative, and they'll be shot through, and they'll deflect downwards. They'll be like, oh, I like you at the bottom, and they'll curve down. If they don't have any charge, then they don't interact with the electrodes at all, and they just shoot straight through. And so what we have to do to detect this is we have to put a screen up at the end, and when the particles hit that screen, it'll glow. And so you're able to tell where it's hitting the screen. So it's kind of a neat little process there. So an alpha particle we know is positively charged because when you shoot it through these electrodes, it deflects towards the bottom, okay? And it's going to hit lower because it attracts down towards the negative electrode. If it's a beta particle, it does the opposite, okay? Negatives attract positives, so it's going to deflect up towards the positive electrode. And if it's a gamma ray, there's no charge on a gamma ray, so it'll just go straight through. So that's how we detect those and how they were discovered. Let's talk about penetration. So alpha is the larger size particle. It's got 2 protons and 2 neutrons, so it's pretty large. Really, a piece of paper will stop an alpha particle. Not a very high penetrating power. It's basically helium. A beta particle is a lot smaller. It's really just an electron. So we're talking, over 1,000 times smaller, almost 2,000 times smaller. And it can actually go right through paper. Like it doesn't even see the paper. It can just fit right through the particles in the paper. It would take a little bit of lead. Okay, a good, half centimeter, like that big, that thick. Maybe like as thick as a sheet of aluminum foil to stop a beta particle. The only hazards for humans really with beta particles is on the surface of your skin. So you can get a really nasty burn. Of course, we all have had sunburns maybe, and that's not so nice. Over long-term exposure, it can lead to skin cancer. The ones we're really scared of that can immediately be fatal are the gammas. Gammas penetrate like cinder block up to a foot. It would take like 10 centimeters of lead, so like that much lead to stop a gamma ray. So when you're around gamma radiation, shielding is really important for humans and not being exposed for a very long time. So how do we detect this radiation? We use a device called the Geiger Counter. It detects ionizing radiation. A Geiger counter has 2 main parts. It's got a sealed gas chamber, and when it comes into contact with ionizing radiation, there's a little chemical reaction that happens with the gas that's in the chamber, and it counts how many interactions per minute. So it kind of clicks. Pretty neat. So let's talk about radiation and you, because there's lots of people who work on nuclear submarines. They work in nuclear power plants. They all have to have radiation badges that absorb whatever radiation their body is so that they can keep track of how much radiation their body receives. So the effects of a single dose of radiation kind of depends on several different things. It depends on how much radiation exposure, what type it was, and the length of the exposure. Time is very important here. So REMs kind of takes into account all of those ideas. You might have heard of RADs. That's the actual amount of radiation. REMs is more like how much radiation, how long was the exposure, what type of radiation was it, and that really determines how harmful it is. So a REM, a dose of 0 to 25 is no effects, like you're fine. But when you start getting up around 150, 300 REMs, things start to get ugly: nausea, fatigue, hair loss, skin reddening. And then if you get a lot of high dose very quickly, then it's almost sudden death. All right, half-life. So we're going to get into half-life. This is a way that scientists can make predictions, because we can't actually tell when an individual isotope is going to radioactively decay. We don't know when alpha, beta, or gamma is going to happen. So if we have a sample that contains lots and lots and lots of radioactive isotopes, we can statistically predict the time it takes for half of it to decay, and that time is called half-life. And we're going to use T, lowercase t, with a little half subscript to denote half-life. And I can put that in here. Half-life, the symbol we're going to use will be T with a little subscript on half, like that. That's our symbol that we're going to use for half-life in all of our problems. So it's the time it takes for half of any sample size to decay. And there's different problems you can do with half-life. Like you can say, what's going to happen in the future? Like if I have a sample of 100 grams, how much am I going to have in 10 years? Or how much am I going to have in 20 years? Or how much time would it take for half of it to decay? How much time would it take for all of it to decay? You can go forwards in time. You can also go backwards in time. You can say, here's how much of this sample I have now. How much would I have had 20 years ago or 30 years ago? And we also use this for radiocarbon dating. So being able to tell how old things are. Once living things always contain samples of the carbon-14 isotope. And so we can kind of work backwards in time and figure out how old those things are. So all this is based on something called a decay curve. A decay curve shows you how much time has elapsed for the radioactive sample and what its mass is. And so notice that it always curves down like this. And that's because in the same amount of time, half of it always decays. And that's why we get that downward kind of curve. So let's say we start out with 20 grams of this oxygen isotope. It's oxygen 15. And we start out with 20 milligrams of it. After 3 half-lives, you can see on the graph, every time we have half. So after the first half-life, we would have only 10 milligrams left. And then half of 10 is 5. So the next half-life, we would have 5 milligrams left. And then after one more half-life, we would have half of 5 is 2.5, so 2.5 milligrams. And we can continue that process. What would you have? What's half of 2.5? Well, it's 1.25. What's half of that? Well, it's 0.625. So after 5 half-lives, we'd have 0.625. So you can just keep having. And this is an example of going forward in time, right? What's going to happen in the future? So let's look at a radioactive sample. This is iodine-131, and it has a half-life of 8 days. So we have a 10-gram sample to start with, it says here. And we want to know, going forwards in time, if I go forwards 24 days from now, how much of it will still be here? How much of it will not have decayed is the question. So the quick way to do this is to first figure out how many half-lives 24 days from now would be. And the way we do that is we say, okay, what is the time? I want to know what's 24. And what is the half-life? What is the half-life? That's 24. And what is the time that I want to know? And that's 8. And if you divide those, you get 3. And that tells you that 24 days from now will be 3 half-lives. So we have to figure out, if we have a 10-gram sample, we have to have it 3 times. Okay, and I just do this in my head. So half of 10 is 5. That's my first half-life. Half of 5 would be 2.5. That's my second half-life. And half of 2.5 would be 1.25. And that's my third half-life. So 1.25 grams is how much I would be remaining 24 days from now. Okay, we can also go back in time You do it the same way, but instead of having it, you double it because you had more of it in the past. So same question, but the question is, what if I reverse time 24 days? How much of the sample did I have 24 days ago? So again, you divide your half-life 24 by the time interval 24 days by your half-life 8, and you come up with 3 half-lives. So if I have a 10-gram sample today, then 1 half-life ago, I would have had twice as much, 20 grams. And then 2 half-lives, I would have had twice that, which would be 40 grams. And then 3 half-lives, I would have had twice that, which would be 80 grams. So I usually just kind of logically do it in my head. Okay, let's talk about radiocarbon dating. So this kind of going backwards in time idea can be used to tell us how old fossil remains are. So it's any living thing can be radiocarbon dating as long as you can get a good sample from it. And the reason why is because radioactive carbon-14 is forming in our atmosphere all the time. Because we have so much nitrogen in our atmosphere, when it gets high up, it interacts with the cosmic radiation from the sun, and there's a little chemical reaction that produces this radioactive isotope carbon-14. And all living things on Earth end up absorbing this carbon-14 in really predictable ways. But once you die, you stop absorbing it. That doesn't mean it stops decaying because it's radioactive. So it collects, the collected carbon-14 in your lifetime starts to radioactively decay, and it's super predictable because the half-life of carbon-14 is 5,730 years. So we can use that half-life and figure out the decay rate, just like we did going backwards in time. We'll use the symbol Y for years and look at an example here. So one of the kind of neat things is you can find this ancient, archaeologists find these ancient remains like scrolls and things like that. And they can say, well, what concentration of carbon-14 does it still contain? It contains 50%. If it contains 50% of the original carbon-14, well, 50% is 1 half-life, right? Because it's always half. So what would it have been 1 half-life ago? How old is the scroll? Well, 1 half-life ago would have been 5,730 years old. So I can tell you how old that scroll is based on the percentage of carbon-14 it still contains. Nuclear chemistry is pretty amazing. So one of the great things about nuclear chemistry is that's how we get a lot of our power. A little over 20% of power in the United States is produced in nuclear power plants. And the process is called fission. The fission process is used to produce electricity by turning water into steam. The steam turns the blades of turbines, and the turbine generates electricity. So it's a nice, green, safe type of energy. There's a lot of controversy over what to do with the spent nuclear fuel. In this class, we're going to get more into the chemistry of it, which is looking at fission. So how do we have these nuclear reactions that produce heat and energy that we can harness and create electricity? Well, it all comes from the splitting of the nucleus. You have to have fissionable material, or material with a large enough nucleus that when it gets hit, instead of just giving off a little bit of energy or giving off a few particles, it actually cracks and it splits in two, just like breaking a cookie. And just like breaking a cookie, you're always going to have little bits and chocolate chips and things that fall. Well, there's little particles and things that come out of this chemical reaction that make it a chain reaction. Okay, so let's take a look at this. So this is a parent isotope, uranium-235. And what happens is it gets hit with a bullet, and the bullet is a neutron. Neutrons have a mass of 1, but they don't have any protons, of course, so the atomic number is 0, and we just use the symbol N. So the 1, 0, N is the neutron. So the bullet comes in, and the uranium absorbs that neutron bullet, and it becomes uranium-236. Now, uranium-236 is very unstable, and there's a crack that happens, okay? So it kind of splits in two, and it's going to produce 2 daughter isotopes, similar in size. One of them is a krypton isotope, and the other one is a barium isotope, and both of those are actually also radioactive, by the way. The interesting part of this is that's not all, okay? It gives off a tremendous amount of energy, and we can harness that energy to turn water into steam and to turn the blades of a turbine and generate electricity. But it also gives off these 3 individual neutrons. And you can see them in the diagram here. They're yellow. They look like little bullets coming out. And I think that what's interesting here is that those become neutron bullets that start more fission reactions. And that's called a chain reaction. We'll talk about that in a second. So a tiny bit of mass is lost in this process. It's called the mass defect. And that little bit of mass is converted into a huge amount of energy. You might have heard of Einstein's famous equation, E equals mc squared. E equals mc squared explains how much energy is produced in this reaction. E is actually called the binding energy, M is called the mass defect, and C is the speed of light. Now, we won't be doing a lot of E equals mc squared calculations, but if you take a physics class, you will learn a lot more about that equation. Here's a chain reaction diagram I mentioned. So each fission that occurs produces 3 new neutron bullets. Each of those neutron bullets goes and hits another uranium-238, and that's going to make 3 more neutron bullets. And those 3 neutron bullets hit 3 more uranium-238s, and they produce 3 more neutron bullets. So it's just like if you and your spouse had 3 children, and each of those 3 children had 3 children, and each of those 3 children had 3 children, pretty soon you have a whole lot of descendants, right? And every time this fission occurs, heat and energy are released. And pretty soon that heat and energy builds up, builds up, builds up, builds up. And if we don't control this reaction, it will produce enough heat energy to actually melt the container that it's in. And we call that a nuclear meltdown. That has occurred in places like Chernobyl and a little bit at 3 Mile Island, also Fukushima during the tsunami that they had in Japan. It is very, very, very hazardous and must be avoided at all costs. And the most important thing are the control rods. To control this chain reaction, because you cannot stop it once it starts, to control it, what they do is they lower these control rods down into the nuclear chamber, and the control rods will absorb some of those neutron bullets, and it prevents them from hitting the uranium isotopes and starting more fission reactions. So you can't stop this nuclear chain reaction. You can only kind of control it with control rods. Eventually, you run out of fuel. So you run out of fissionable, useful material to produce the heat energy that you need to generate electricity. And so after that, they say that the fuel is spent. And what they do with those spent cartridges is they store them, usually on site, or they'll out west they'll ship them to a mountain called Yucca Mountain, and they'll store it there, way far away from people. They have to bury it in concrete because even though it's not useful to generate heat energy anymore, it is still very harmful and very radioactive and should never ever be near people. And it will be for many thousands of years. So we have a lot of debate in the country about what do we do with this spent nuclear fuel? You know, once it's used up, what do you do with it? It's not safe. How do we contain it? What can we put it in that will last forever? There's nothing. So there's a little bit of debate about that. Okay, opposite of fission is fusion. Now, fusion does not happen naturally on the Earth. We can do it in labs and small scale fusion. But in fusion reactions, smaller nuclei actually come together and produce something larger. And most of the time, they'll also spit out a couple of particles just to keep a stable nucleus, and they will release a tremendous amount of energy, much more even than fission. So fusion occurs in the sun and, of course, any other stars. All the light, heat, electromagnetic radiation that we get from our sun and other stars, all of that comes from this giant fusion reaction. As long as there is fuel in the form of hydrogen, fusion will continue on our sun. Eventually, our sun will die. It will run out. We have a nice middle-aged sun, so we got like 4.5 billion years before that happens. So why can't we do it here on the? If it produces all this great energy, why can't we use it? Why can't we do that? Well, we can sort of. It's used in some, sadly, in some nuclear missiles, nuclear bombs. But as an energy producing source, it's not great. It requires a lot of heat energy to get it started. Think about how hot the sun is. And that's not going to be easy to do here on Earth. And it requires that we kind of contain the heat energy that it produces in some efficient way. And it's very hard to contain heat energy. You know, heat travels from place to place just through air and contact. So, you know, how do you trap heat? It's very difficult to do. So all of our attempts at using cold fusion as an energy source have really failed, sadly enough. And not to end on a sad note, but that reaches the end of my presentation on nuclear power. Thank you for joining me.